Hi, I'm Ron, and welcome to Best Practices in Automated Testing. First, I have a confession to make. It took me years to figure this stuff out, and the help of some brilliant people. It also helped to have seen it done, badly, any number of times. So today, let's get you to the finish line so it doesn't take the years it took for me. So why automated testing? Well, if we're working on an application of any complexity, we want a good way to verify the correctness of our code, and that the code we're shipping is free of bugs or unexpected behaviors. And we want to keep doing that over time, even as that code changes. And last, we want to do all this efficiently to best leverage the resources of the team. Sounds great. So what can go wrong with that? Well, I call them the 3 B's. So first, bloated. That's an automated test suite that's slow. Many test suites take hours and hours to run, which means that instead of running it more routinely, even during the development process, we hold off until as late in the process as possible, say just prior to shipping. That isn't optimal at all. Second, brittle. A test suite where tests break when underlying implementation changes, whether it's in business logic or user interface. And third, bifurcated, which typically means 2 separate test suites. One test suite by developers, which lives in the codebase, and usually another test suite by QA, which lives somewhere else. So not only is there duplication of effort, but also multiple sources of truth. And if you include testing efforts across multiple platforms, it's even more. So bloated, brittle, and bifurcated. And of course, none of these are optimal. To understand how we might improve this, let's consider the flow of a development story as we probably do it now. First, the story is created by the product owner, along with some acceptance criteria. Then it goes to the developers who implement the story from there. Then the code they've written goes to code review or peer review, and it's reviewed by the other developers. Next, it goes to QA, which seeks to verify that the implementation does what was specified in the acceptance criteria. And from there, of course, the app goes out to users. Now, with those different points in the process, let's consider the cost of fixing a bug. Well, let's start on the right. If a bug gets out to the user, well, that's not optimal at all. It means that the user may not be able to do what they want or need to do, or there may be unexpected behaviors. So if we can catch that bug a step earlier, that saves the user the time and hassle of dealing with that bug. That's definitely better. But we can do even better than that. Let's say that bug is caught in code review. That means it never gets to QA, and they don't have to spend time and energy tracking it down, which is even better. Or if we can find that bug during development itself, that's even better still, because it saves the dev team the extra effort of addressing the bug in code review, or maybe later in QA, or by the end user. So that's close to ideal. But what if we could discover that bug way back during the writing of the story itself, and in its acceptance criteria? Well, that would save a whole lot of work by the rest of the team, and also spare the user as well. In order to do that, let's consider what's being looked at in each step of this process. The product owner is creating a story and acceptance criteria in a project management system. The developers are writing and looking at code in their integrated development environment and its code editor. In code review, the dev team is looking at a code repository, probably within a web page. And so in the entire process so far, the artifacts people are looking at are actually textual. It's human-readable text. But after that point, something changes. So let's draw a line right there. After that point, that human-readable text becomes a binary executable, only readable by a machine. And that binary is a mix of both behavior and user interface, all rolled into one. And so at that point, that UI is the primary, if not the only, means for QA to test that underlying code. And so QA is very limited to a graphical user interface, and that's a big limitation. Now, we also said that testing is typically bifurcated. So let's look at how QA approaches QA. They'll start by writing out test cases to verify the functionality of the application, and then typically they go through those test cases as a manual process. So tapping on a screen, going through different scenarios, and then repeating again and again. That gets repetitive and tedious, performing many different test cases over and over again. And so understandably, there's a desire to automate those tests, and that does solve the issue of repetition and tedium. By teaching an automation framework how to do the same things, tapping areas on the screen, entering certain text, pushing a button, and so on, well, that has to be better, right? Now it's automated. But remember, it's still based on a graphical user interface, and so those tests are still brittle. Because when the UI changes later on, maybe part of an exciting new look, those tests can break. After all, they were based on the previous and not the new version of the GUI. And there's another issue as well, even when it is automated. Computationally speaking, UI-based testing is actually relatively slow. So here's another graphical user interface. It's composed of views and superviews and subviews, which may contain a number of different UI widgets, some of which have graphic elements. And all the UI widgets are constructed with bitmaps that hold the contents of every one of those pixels that are on screen, which need to be rendered. And each pixel must be stored somewhere in memory, and those bitmaps each take time to construct. Now, all that creates a lot of overhead and uses a lot of memory and takes many CPU cycles in order to construct all those views and put each of them on the screen. And so, in order to run each test, we're creating a hierarchy of views, which may also require navigation, and are contained in some sort of a window on a screen, encapsulated in an application, which runs on a device, whether it's an actual physical device or a virtual device, say a simulator or emulator. And now consider what happens if we need to start fresh before each test or set of tests. How long does it take to quit and rerun an application? Or reboot a device, maybe with a reset? 3, 5, 10, 20 seconds or more? This is something I think of as kind of a big O notation for automated tests, which is just a way of expressing how long it takes to do the work as we do more and more of a certain type of task. If we've become diligent about creating automated tests for our different use cases, and we're testing happy paths, unhappy paths, edge cases, and corner cases, over time a thorough test suite for an application can easily encompass dozens or hundreds or even 1,000 or more of these tests, which verify the different functionality of the application. So multiply all that out, and soon you're talking about a test suite that takes hours or even tens of hours to run. It just does not scale well. And that inefficiency when having to test through a UI is inherent in the very nature of a graphical interface. And so that's why our UI-based test suite becomes not only brittle, but bloated as well. And the longer the test suite takes to run, the less often we'll run it. So what's the alternative? Well, consider business logic. Business logic is just pure logic. It's pure machine instructions that can run as fast as the CPU. And the CPUs in our smartphones nowadays are very fast. They can do billions of operations per second. And so if we could somehow have our tests talk directly to that business logic instead, then we could do hundreds or thousands of tests, and those might just take minutes to run, not hours. So how do we talk directly to business logic? Well, that's dependent on how the codebase itself is organized. So let's switch over to development now and look at how automated testing is typically handled by developers. TDD, or test-driven development, is where developers are working in the code and writing automated tests while writing that code. And in a general sense, this can be a best practice. But the way it's frequently done and even taught often has anti-patterns of its own. Because this test code lives in the codebase and is run alongside the application code itself, it may indeed be fast, but still end up brittle, because those tests are often oriented towards very specific details of how the underlying code is implemented. And that's a problem, since later on, when those implementation details change, those tests have a tendency to break, and that can be very discouraging. Or even knowing that the test may break can discourage refactoring that code in the first place. Neither of those is optimal. So let's look at how this developer-level testing might be done differently. There are different styles of programming, and recently we're reminded of one style called declarative, like in SwiftUI on iOS and Jetpack Compose on Android, as distinguished from the imperative style of programming. So what are those? Well, imperative is when we specify how a task is to be done. Declarative lets us specify what the task is to be done rather than how to do it. So let's look at how this works, and we'll use an example from real life. So here's a declarative request. After work, please bring home some milk. That's about as simple as it gets. And everyone knows what we mean by that. But what would it look like if we used a more imperative approach? Well, it'd be more like a series of instructions, potentially very detailed, maybe like this. When finished at work, walk out to the parking lot, find your car, unlock the car, get in, put the key in the ignition and start the car, drive out of the parking lot, turn left, etc., etc., etc. And those instructions might work just fine. But what happens if, say, there were construction and a detour on Main Street, or the dairy case was moved within the store, or they were out of milk entirely, or any number of other changes? These instructions would break down. They wouldn't return the expected results. They'd no longer work, and we'd have to rewrite them to tell the underlying code what to do and how to do it. And if we did take this very low-level approach, we could easily be double-checking at that level of detail as well. So in our example, maybe like this. And if this seems a bit silly, well, we might take a lesson from that. Because what is it that we're really trying to achieve? What really matters in this scenario? Is it to drive down the street? To go to the store? To spend money? Aren't those really just means to an end? Aren't they just implementation details? What is it that we actually care about? What are we trying to accomplish? Could we focus on that result instead? There is a different approach to implementing stories and the tests that go with them that operates at a much higher level. It begins with the story requirements themselves, and it's called BDD, or behavior-driven development. And here's the format of a behavioral test, one of the scenarios we're testing for in our code. Each scenario has a name, and then given one or more starting conditions, when we take a certain action, then we expect certain ending conditions. So here's an example for the simple scenario we were looking at a few minutes ago, a successful login. Given that I am logged out, when I provide my username, and I provide my password, then I expect to be logged in. Notice we're focused on the results of the scenario, not all the minutiae of how the underlying logic does it. And that's valuable because it frees us up from all those details, and we can operate at a higher level of abstraction. Now, teams that are used to doing UI-based testing, out of force of habit, tend to stick with that paradigm, even in describing behavior. So, for example, you may see test cases written like this. Again, a successful login, but referring to screens and text fields and buttons and more screens. That's not how we want to do our behavioral tests. Because remember, when we focus our tests on user interface, then our test suite as a whole will end up bloated. It'll take a lot more time to run. And because user interfaces change over time, our test suite would also be brittle. So we want to test for these scenarios in a more general way. Let's break down how that happens. So here's our scenario on the left, and the right is what developers might recognize as a state machine, a finite state machine. We start with a precondition, that's our given. Then we do a transition, say in this case by providing a valid username and password. Then we expect a certain set of post conditions, namely that we become logged in. And our keywords are given, when, and then. Now, depending on the specific style of BDD, you may see other words used like arrange, and act, and assert. But it's all the same thing. All right, let's look at another scenario. How about one possibility for an unsuccessful login? Given that I am logged out, when I provide my username, and I provide the wrong password, then I receive an error message, and I am still logged out. So that's another scenario. Okay, let's try one more just to make sure we get the hang of it. Let's say we have a shopping cart, and our scenario in this case is to add an item to an empty shopping cart. So the precondition is that we have an empty shopping cart. The transition is that we add an item, a specific item. And then we expect that the cart now has one item, and the item in the cart is the same one that we added. Simple enough. Now, just a point of terminology, BDD can actually be thought of as a specific, more modern subset of TDD. They're both development driven by testing. It's just that BDD focuses on behavior rather than on the typical implementation details. So how do those two styles of writing tests compare? TDD is usually written in code, and so it's understandable by developers, though less understandable to non-developers. It's often oriented around lower-level implementation details, and therefore it's brittle. It may break when those implementation details change. By contrast, BDD, behavior-driven development on the right, is written in plain English, and therefore it's understandable by everyone on the team, including product, developers, and QA. It's also self-documenting. It's oriented towards high-level use cases, and therefore, as things change over time, it's more robust. So we keep alluding to writing tests in ways that do not depend on a user interface. Well, where we're going, we don't need the UI. Well, a little bit, but actually not that much. So let's think about the business logic inside our application and how we might communicate with it. To do that at that higher level that we want to depends on having a clean architecture. And how to do that well is a whole nother talk unto itself. But at a basic level, another analogy might help us to understand. Well, quite a while back, I was reminded of a scene in the original series of Star Trek. It was from an episode called Spock's Brain, and there's a really interesting idea in there. In the story, an alien actually steals Spock's brain, removes it from his body, and then uses his brain to run the machinery in an underground city. And when our heroes track it down, they're conveniently able to communicate with Spock's brain directly over their communicator. And he describes the sensation of being just, as they call it, a disembodied brain. That his consciousness exists in kind of a void, with information coming in, which his brain then processes and sends off the results. Now, the interesting thing is that Spock actually has no idea where the inputs come from or where the results go to, just that there's this constant flow of data in and out and being processed in some useful way in between. And so there's a key concept we can take some inspiration from. It's something like this. Our business logic is the smarts of the application. It processes information and gives us useful results, kind of like that disembodied brain. Now it receives inputs from somewhere, and it doesn't know where, and when it processes those inputs, it then sends off the results to somewhere, and it has no idea where it's sending it to. And that flexibility will really come in handy, as we'll see. And as we talked about, our business logic, which is the underlying smarts of our application, the thing that makes decisions, can actually be very fast. It runs at the speed of the CPU. Well, that's assuming we can insulate it from slower dependencies like service APIs and databases, and there are ways to do that very effectively. But if our tests talk to a graphical user interface, then they become a lot slower. So what can we do? Well, remember, we're now writing our test scenarios to ignore the user interface completely. And here's where that flexibility we talked about really helps. If we construct our application architecture so the business logic gets its input directly from the automated tests instead of the UI, then those automated tests run really fast. There's another thing that behavior-driven development allows us to do. Remember, we talked about how testing efforts are often split off between development and QA. So let's think about the different roles on the team and what their strengths are. The product owner is good at understanding business requirements, developers are good at implementing functionality, and QA is good at finding ways to verify that functionality. And if we can get everyone speaking the same language as we do in our BDD test scenarios, then all of the members of the team can actually collaborate on writing those scenarios, the acceptance criteria for our stories, together. And in BDD, that's sometimes called the three amigos, the product owner, QA, and developers, working together to write those scenarios. And so one of the things BDD offers us is the ability to integrate QA into the development process itself. No more duplication of effort after the fact. Instead, they help developers create a code base that actually QAs itself. And part of the goal of moving tests earlier in the development process is tightening up that feedback loop to get QA-type feedback not later after the build, but as early and often as possible. And if we can run our test scenarios fast enough, then the developers might actually be able to run those tests while they're writing the code. This is the essence of development that's test-driven, a process driven by and guided by the tests themselves. So imagine them having a series of status lights for the code they're working on right now. The effect is almost magical. It's like having a coach guiding them over the shoulder, letting them know exactly when their code meets the requirements. And later on, when implementation needs refactoring or updating, it ensures whatever changes are made by whoever makes them haven't changed the results. Imagine no regressions at all. This is the central goal of test-driven development, having tests that drive our development process, and that's a good thing. By the way, QA engineers, QAE, might even work directly on that part of the code base. Not only is that more holistic and better integration within the team, it can even provide future growth potential for those QAE that may be interested in doing development itself. All right, now there are several types of automated tests we can use in our code base, and they test several different aspects of the system. Let's look at those. So far, we focused on behavioral tests, as this will be the majority of our test suite. If done well, they're performant and not brittle, and they'll serve us well on into the future of the project. There's also what we can call contract testing. That's a simple sanity check to make sure we can communicate with other parts of the system we depend on. So, for example, we may need to fetch data from some service APIs. And so we can throw in a handful of tests just to make sure the services are there and seem to be doing what they're supposed to. Now, we don't want to test those services comprehensively for two reasons. First, compared to pure logic running on the CPU, service calls are much slower. We don't want too many of those to slow down our test suite as a whole. And also, we shouldn't need to do much testing of services. In order to scale our development effort, we have to assume the team who developed the service is doing proper testing of the code they wrote, which is, after all, just another application. So minimal testing there, just to make sure nothing's obviously broken. And also, there's another kind of contract. We've said we're not focused on testing UI, but we do have a UI, so we probably want to test it somehow. But we don't need to run through all our different use cases there, because we're testing those scenarios directly with the business logic, where the actual decisions are made. Remember our disembodied brain? So what is it that we need to test for the UI? Here, if we follow another clean architecture principle, we can think of the UI as simply a dumb input-output device. It accepts input from the user, which gets sent to the business logic to be processed, and then takes the results from the business logic and just shows them on the screen. In other words, to paraphrase my hero, Uncle Bob Martin, the view layer is dumb as a rock, meaning it doesn't make any decisions at all. Then our goal is like one of those electrical continuity testers. We simply make sure it's wired up, that each widget in the UI is connected to the appropriate inputs and outputs for the business logic, and that's it. That's the minimal automated testing specifically for the UI we need to do. A third type of automated testing is end-to-end. That simply fires up the system as a whole and runs through a handful of basic use cases, again, just to make sure everything's there with no obvious problems. But we don't do much of this for the reasons already mentioned about performance and distribution of responsibility amongst the teams. So this is just kind of an automated smoke test. So what do these look like together in our automated test suite as a whole? Here are some recommended allocations. Behavioral tests should be the vast majority of our test suite, say 80%. These test all the scenarios in our business logic and do it exhaustively and performantly. Contract tests might be about 10%, again, just to make sure our dependencies are there and seem to work. And end-to-end tests make up the remainder of our automated test suite, essentially smoke tests to make sure the system as a whole seems to be behaving as expected. Notice we haven't used the term unit testing. We're not actually interested in testing units of code. We don't want to become tightly coupled to particular classes, functions, etc. Remember our supermarket analogy? We're only interested in end results. That keeps our tests nimble and immune from the details of how that underlying code works, and our tests do that on into the future, even as that implementation changes. We also haven't used the term integration testing. The word integration is used by different people to mean different things, and so we've deliberately avoided that term in favor of more carefully chosen language. And that's it. That's our new, improved automated test suite, performant, robust, and integrated across our entire team. By the way, there still is a role for QA after the build is done and before shipping the app. But given all the QA we've done now up front, this is pretty minimal by comparison. We are shipping a binary, and it does have a graphical user interface. And there are non-functional requirements we haven't talked about, like making sure everything looks good on the screen according to the design. So it's never a bad idea to do some smoke testing manually, but it does not need to be comprehensive because we've designed all that testing into the codebase itself, and those ran early and often, long before we did the build. So by taking the approach we've talked about here, we get some key benefits. The team becomes more holistic. QA is integrated into the development process itself, and everyone speaks the same language, which we use to define our acceptance criteria together, which paves the way for a smoother process in development and with code that becomes self-documenting. Our automated test cases do the work of exhaustively testing our functionality for correctness, and they do that over and over again, automatically, for the life of those features in the codebase. Our implementation is flexible. Refactoring the code doesn't break the tests, so we can continue to iterate on that code and build on our automated test suite without the usual fear of obsolescence. And by taking a high-level approach to development and testing, it also encourages an application architecture that's loosely coupled from implementation details. And that decoupling includes the UI, so we can adapt our user-facing designs as needed. And with all these improvements, we can get that much closer to the ideal of, when the tests pass, we ship. And finally, here's a picture of what our testing efforts looked like before, and now what we have to look forward to. Well, I hope this session has offered a few useful ideas that help achieve our goals for automated testing and software development as a whole. One thing to keep in mind, we talk a lot about Agile and Agile practices in our day-to-day work. And if we do it right, it's really not just about how we do development. It's a means to a greater goal. If we become good at making not just our process, but our code agile, then the business itself becomes agile and can respond more efficiently to new opportunities. And if the business can do that, it enhances not only its own, but our success as well. I want to acknowledge some very special people who were the source of many of the insights we've talked about here. People with a vision of the next generation of software development and testing. They're the real thought leaders, and I'm very grateful to have collaborated with or been inspired by them all. Big thanks to them and to you for watching.